Hello and welcome to another video, this time on question 3 from the stats paper in June 2018, and it was a probability question. I'm just going through the probability questions basically for the next half an hour. Okay, so let's have a look at this one. In an experiment, a group of children have to throw darts. I love darts. Okay, great. For each child, the random variable h represents the number of times the dart hits the target in the first 10 throws. So I guess it could hit 0 times, 1 times, 2 times, all the way up to all 10 times. Now, Petal's going to model this as a binomial distribution with the number of trials 10 and the probability of success 0.1 to state two assumptions you need to make. Now they're really asking you what assumptions need to hold for a binomial distribution to be appropriate. Well, each trial must be independent of the next, so you need to say each throw is independent of any other throw. And what we're saying there is that it's not the case that the throws are going to influence in any way your chance of hitting the target on the next throw. So each throw is independent of any other throw. Now we can talk about whether that's realistic or not. I would say possibly not really, because quite often people get put off with what's happened in the last throw, or maybe because of practice they get better and better and better. So there's lots of reasons why that condition might hold, but that's the assumption she's made. And another assumption, another thing for binomial distributions is that the probability must remain constant. The probability of hitting the target must remain constant. There are a couple of other things you could get for this. A couple of other ways you could get the marks. You could use the other things as like a list at the start of the binomial chapter in the textbook. There's a list of conditions for when the binomial distribution is appropriate. You could say that there's only two possible outcomes: hit the target or not hit the target. That's fairly obvious here that that's going to be the case, but I suppose it could hit on the line and be ambiguous. You could also say that there is a fixed number of trials. There are indeed just 10 trials here, a fixed number of trials, but that's fairly obvious that holds in this case. They always want the independence one, basically. They always stick that one down first, and then the probability doesn't change, it's always constant. So there we go. Okay, using Petter's model, find the probability that h is greater than or equal to 4. Now, if you've got the new calculator, which everybody seems to have now, you want to do this. Calculators work with binomial CDF, yeah? You want binomial CD, as they called it on the calculator. And the reason you want binomial CD, and I'm often asked, when do you use binomial PD, when do you use binomial CD? Well, PD is when it's equals, and CD is when it's less than or equal to. Now, we're going to have to flip this, therefore, and make this probability that h is greater than or equal to 4 is 1 minus the probability that h is less than or equal to 4. You can then use your calculator to work out the probability that h is less than or equal to 4. It should come to 1 minus 0.9872. And so the final answer is 0.0128 to three significant figures. Yeah. Quick point that if you have got one of the really good graphical calculators, you could just get that answer just by plugging that in, and that's fine as well. It's only a one marker. Okay, next bit. For each child, the random variable f represents the number of the throw on which the dart first hits the target. That's immediately interesting to me because what they're describing here is something called a geometric distribution, where you're looking for the off success to occur on the nth throw or something like that, or so the first, in this case the first success to occur on the fifth throw. That is a geometric distribution, but you don't need to know anything about that. All you need to think is we want to miss and then miss. And each time you either hit or miss, don't you? Think of this as a tree diagram kind of situation, but one where it's not worth drawing out most of the tree diagram. You want miss, 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 hit. That way, you definitely hit on the fifth throw for the first time, because it's about when the dart first hits the target, in which case you have to miss, 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 then hit. And if we want to miss, we've got a probability of doing that of 0.9. So we're going to have 0.9 to the power 4 times by 0.1, and that will give you 0.0656 to three significant figures. But yeah, that's an interesting distribution to me. If you're ever looking for a success to occur, like on a certain trial, think about penalty kicks or something like that. Let's say you're taking 8 penalty kicks and you're finding you want your random variable to represent the particular penalty kick where you first score. Well, you'll need to miss, then miss, then miss, and then hit, and that's the way you'll always do that kind of situation. Look out for it. It does pop up in 1 or 2 questions in the textbook, but not that many. Okay, finally we get to this. Now this is a bit more confusing. This is essentially describing like a discrete random variable. He first says that no child will need more than 10 throws. Okay, so 10 throws is the maximum. He models P of f of n as this, so he's telling you how to model it. Yeah, and if you're ever unsure what the probability should be, or if ever to ask you to find the value of a constant in probability, try drawing a table, of n and then the probability that f equals n. Yeah, so we've got, he could firstly, what is f actually representing here? Well, we're already told it's like the number of the throw on which the dart first hits the target. So it could hit on the first one, or the second one, or the third one, or the fourth one. And you could write this table all the way up to 10, and I think most students probably would be happier doing that. I'd probably just put ... myself, because you'll get a pattern pretty quick. Yeah? Okay, first probability, because you're doing 1 minus 1, that's 0. 0 times alpha, you're going to get 0.01 for that. Yeah? But for the next one, n is 2, and so you're doing 2 minus 1, you're timesing that by alpha, so you have 0.01 plus alpha. Then here you're obviously going to get 0.01 plus 2 alpha. Yeah, I'm going to put ... in here. Now you can fill the whole table if you like, but on the last one you're going to have 0.01 plus 9 alpha. And so we're going to find the value of the constant a. Well, we're just going to add all those together, and then we're going to have 10 0.01s, and then we're going to have alpha plus 2 alpha plus all the way up to 9 alpha, and that should equal 1. Okay, 10 times 0.01 is 0.1, and if you add up the numbers from 1 to 9, it actually comes up to 45, and so we're going to have, and you can do that quickly on a calculator, or you could use an arithmetic sequence if you want a sum of an arithmetic sequence, because this is first term alpha, common difference alpha, or you could just use a trick like, pairing up the terms. Alpha plus 9 alpha is 10 alpha, 2 alpha plus 8 alpha is 10 alpha, all the way up to the middle one, which is 5 alpha, so it's going to give you 4 lots of 10, which is 40, plus 5 alpha in the middle, 45 alpha. So what have we got here? We've got 45 alpha is 0.9, because that's 0.1, take away from 1, you get that. So alpha is 0.9 over 45, which equals 9 over 450, but both of those are divisible by 9, and so you're going to get, let's write it down slowly, I suppose, divide top and bottom by 9, you get 1 over 50, which is 0.02. Okay, we've found the value of alpha. Using Thomas's model, find the probability that f equals 5. Well, we're just going to plug in f equals 5 now. So the probability that f equals 5 is going to be 0.01 plus 4 alpha. 5 minus 1 is 4, and so that's going to be 0.18, because that's 0.08. Add them together, you get 0.18. Oh, hang on. No, sorry, I made a slight blunder there. 4 times 0. Yeah, I've made a mistake with the tens and the units there. Let's actually write that down again. That's poor maths in my head. 4 times 0.02, that's 0.09. That's better. Sort it out, Nichols. Right, okay. Part F. Explain how Petter's and Thomas's models differ in describing the probability that a dart hits the target in this experiment. Well, the way they differ is clearly in Thomas's model, they're actually getting better at it. They're getting more likely to hit the target. So that's probably what I would say. Petter's model doesn't assume that they're getting any better. But Thomas's model assumes that they're gradually improving. It's only a 1 marker, so that'll do. Okay. They're improving. So it's a slightly weird probability one, this question. Normally you get a Venn diagram. It's sort of a tree diagram one, but not quite. It's kind of a mixture. I hope it makes sense so now if you're worried about it, and yeah, keep up the hard work. Stats is difficult. Do practice it.